Hello, this is Mini Project 1 Thristor Heat Sink Design by Christopher Bory and John Miller. So for an overview, this is what we're going to be talking about. We're going to start with background information, then we're going to go into design considerations, and we will further go into how we analyze these design considerations to assess whether they met the given parameters in a steady state and transient analysis, as well as a mechanical analysis, and then we'll go over our results real quick. Okay, so the problem statement was given as a solid state thyristor gate driver. We were told to design a cooling system that diffuses a constant application of 500 watts for a time span of 10 seconds. The cooling must be double-sided in order to maximize the surface area of to diffuse the heat, and it must satisfy the conditions as shown in the table 1 on the screen. Um, Overall, when we were deciding on what we wanted to do for materials, we overall the first thing we decided was that the best cooling system to use was a heat sink. The first task in this was to choose the material composition of the cooling system. Copper, aluminum, and silver were considered and weighed based upon their thermal and mechanical properties and their cost of manufacturing. In the end, copper was chosen because of its low cost and high thermal conductivity, although silver was not much more thermally conductive. It was at a much higher cost. As well, aluminum was at a low cost, but was a lot less thermally conductive. So that's why we ended up choosing copper. After weighing a bunch of different design options, a cylindrical fin design was chosen, similar to that as shown in the figure on the screen. The dimensions provided were analyzed and adjusted until the design met the parameters. On top of this, we decided to choose a low number of fins in order to have a ease of manufacturability. So during the steady state analysis, it was assumed that the Thristor heat sink system um, had no radiative heat loss. On top of this, there was steady state one-dimensional heat transfer and forced convection as well. The analysis began by understanding the surface areas of the fins, base, and as well as the total surface areas. These came out to 0.00346, 0.00159, and 0.0465 respectively. They were used then to find the fin efficiency and the overall efficiency. These turned out to be 0.9604 and 0.9617, roughly 96%, respectively, for both efficiencies of the fins and the overall efficiency. Along with the provided resistance values that were shown in table 1 on the background information slide, they were also shown here in how we had to adjust them to a 1/2 analysis, since we only analyzed 1/2 of the system. On top of this, we had to account for the conduction of the base, as well as the resistance due to the fins, shown in the equations on the screen. Those respectively came out to 0.0212 and 0.2314. These were then combined and added in order to come up with a total resistance value of 0.2682. These resistances were then related to the heat flux equation, as well as the ambient temperature and the heat flux of in terms of half of the system, which in this case would be 500 divided by 2, or 250 watts. After solving for the temperature, it came out to be 117.05 degrees Celsius.
In some cases, a transient analysis can be done using the lumped capacitance method. In order to determine whether or not this method can be used, the Biot number had to be calculated. You can see this calculation at the top of the slide, for which the result was 0.013. And less than 1 means that the lumped capacitance method can be used. Using conservation of energy equations, assuming no heat loss through the radiation, the constants A, B, and theta were determined. After integrating from 0 to 10 seconds, simplifying using the constants, and plugging in the value of A and B, the temperature was determined to be 112.516 degrees Celsius. After that, the 500 watt heat flux was used to determine the junction overload temperature, which is 124.061 degrees Celsius. If we move on to the mechanical analysis, next, the heatsink had to be able to withstand a clamping force of 40 kilonewtons. Assuming the force is distributed on only one side of the heatsink, negligible stress and no moment forces, and using the cross-sectional area of each fin and the number of fins, the stress in the fins was calculated to be 9.794 megapascals. As this is far less than the 70 megapascal yield stress of copper, it is safe to predict that the films will not deform under this 40 kilonewton stress. To recap, the surface temperature of the fins is 117.05 degrees Celsius. The temperature at the junction between the thyristor case and the heatsink is 124.06 degrees Celsius, and the stress in the fins is less than the yield stress of copper by a factor greater than 7.
Here's our works cited based upon the images we provided, as well as the work distribution on the overall solutions of the problem statement.